Hello, this is Mr. Ferris. This lesson is on continuous growth and the number E. It's highly recommended that you have a worksheet or at least a good piece of paper, but hopefully you have the worksheet that will just allow you to write down answers and not questions. And so hopefully you have that and follow along as we go. One thing I might just warn you, this is going to be a little deep. There's lots of examples and a few new things. So this might be one that you'd want to break up into two pieces possibly, since there's a lot of information here that I'll be giving you. First of all, let's talk about this curious number E. You may have seen this E if you've studied logarithms before. And this is what it is. By definition, it's actually this, which looks a little imposing, but if you just think about it a little bit, this is the summation of a bunch of things as k starts at 0. So in other words, the first term that you would sum would be 1 over 0 factorial, which is 1 by definition. And since you have a summation sign, you're going to add the next one. The next one would be a 1. If you plug in a 1 for k, it would be 1 over 1 factorial, and away we go. Another way to look at it, of course, would be, if I could just do it this way, this is what it would be, and it's forever and ever. In other words, you add up an infinite number of these fractions, and magically it turns out to be this crazy number E. E is a little bit like pi. It's irrational and goes on forever in a decimal, never repeats, never stops. So what is the big deal about E, you might ask? Well, I'm going to hopefully show you some examples of where E actually makes things much, much easier in math to calculate certain things. For instance, in compound interest, the number E will come up. But first, let's break this down into some simpler problems. So follow along as we go. We're going to start simple and work our way up to more complex. So we invest $1,500 in a 6% APR. APR just stands for annual percent rate. So we want to be comfortable with that acronym. APR always stands for annual percent rate. So we're investing $1,500. That's the percent. And we're going to do it just for 1 year, again, to keep things simple. Let's calculate the balance just for that 1 year if the interest, first of all, is compounded annually. For annually, that just simply means that you just calculate it one time, and it's one time at the end of the year. So our balance will simply be $1,500 plus 6%. Well, remember, though, the pre-cal way of adding 6% is to multiply by the factor 1.06, and that would give us a grand total of $1,590. So in other words, we've earned $90 interest on that $1,500 over the course of 1 year. Now let's make this a little more complicated. Let's compound the interest semi-annually. And by the way, the word compounded just means calculated or computed. So what we did here, we calculated or we computed the interest one time at the end of the year, and we added 6% and got $1,590. But now we're going to consider that we're going to compound it semi-annually. That just means you're going to calculate the interest twice. Instead of just once, you're going to calculate it twice. So we would calculate it at the halfway mark, which would be 6 months, and then calculate it again at the end of the year. So we would start again with a initial amount of $1,500. Sometimes it's called the principal. And we're going to compound it twice. Well, okay, let's think about this. Compounding twice, you might think, well, okay, so 6% and another 6%. Well, no, because we're told that it's 6% annually. That's for the entire year. So if we're going to compute it halfway through the year, we're only going to get half of that interest at the halfway point. So in other words, after 6 months, you're only going to get 3% interest, half of the 6%. So at the 6-month point in time, we're going to multiply by 1.03. That gives us half of the interest. And then at the end of the year, we're going to add 3% again, and that gives us the other half. But of course, because of the way the math works, we don't end up with $1,590. We end up with $1,591.35. So you see what's happened. By compounding it twice, even though you're only growing it by half of the percent each time, this second 3% increase is on a bigger amount. Whereas over here, the 6% increase was only on the $1,500. But the the way we did it this time, the first 3% interest was on the original 1,500, but the second 3% interest was on a number a little bit more than 1,500. So therefore, we get just a slightly bigger balance at the end of 2 compoundings. And that's one of the advantages of compounding it more than once a year, is you get just a little bit more interest out of the deal. All right, so let's go one more. How about if we compounded this monthly? Using the same thinking, we're going to calculate our balance by taking our principal, which is $1,500. And, okay, now we got to think, because, yeah, we're going to compound it monthly, but we only can get 6% total over the year. So one way we might want to break this down is we're going to take that 6%, but you're only going to get 1/12 of it every month. Now, I'm going to write it like this. Now, I didn't do that before because it didn't seem necessary, but what I'm building here toward is a pattern that we can use for even more compoundings than even just monthly. So if we go back to here, the 1.03 times 1.03 was really 1 plus half of 6%. Whereas now we want to do 1 plus 1/12 of 6%. And we want to do that 12 times. Every month we're going to compound 1/12 of the interest. And so this is the formula that becomes the heart of a compound interest formula. You're going to be doing a little bit of interest, in other words, a fraction of the original interest every month for 12 months. And if you calculate that and compute it, it turns out that the grand total is, again, just a little bit higher, $1,592.52. So once again, we've gained just a little bit more money. Not much, but just a little bit. In fact, just a little over $1 looks like we gained by going from 2 compoundings a year to 12 compoundings a year. In fact, right here might be a good time to calculate something. Notice that 6% interest, exactly 6% interest, is $90. And that was the name of this. The name of this interest rate was a 6% interest rate. And so we got the exact amount. We got exactly 6%. So we got $90. $90 is what we would call the nominal interest rate. In other words, that's the name. It comes from the root word NOM, and that means the name. So the name of the interest rate was 6%, and we got exactly 6% when we compounded it just one time. But when you compound it semi-annually or you compound it monthly, we get more than $90. $90 would be exactly 6%, but we got a little more than 6%. And this little more than 6%, whatever that is, that's called the effective rate. In other words, that's what you really got. So you effectively got a little more than 6% because the compounding was more than once per year. All right, we're going to ramp this up just a little bit more. Now we're going to compound it daily. So our balance is going to be the same sort of pattern. Hopefully we've been following the pattern. The balance is always going to be the principal times, and if you follow the pattern, it's 1 plus a fraction of 6%. What fraction is it? Well, for compounding it daily, that would be 365 different compoundings. So we've got to take 1/365th of 6%. That's going to be the amount of interest that we earn just in that one day. And of course, we're going to compound it every single day through the year. So we're going to be taking that to the 365th power. And we gain just a tiny little bit more. So now we have $1,592.75. So we've grown just a little bit more interest, not much, but just a little bit more interest by doing it daily. Well, let's ramp it up one more step. Let's go minutely. Let's see, how many minutes are there in a year? That's kind of a big number.
525,600 minutes.
Well, there you have it. So now we know what to write. The balance is $1,500 times 1 plus 6% divided into the number of minutes in a year. 525,600. And we're going to compound that 525,600 times, and your calculator should handle that. And it's going to be $1,592. And when you round to the nearest penny, it's still 75 cents. So notice we didn't even really effectively gain anything. So you can see there is a limit to how much interest you're going to earn. By the time you get to minutely, you don't really gain anything. You only gain something in the, I guess what would be kind of the extra decimals that perhaps would be there. So we don't really gain much by going between daily and minutely. However, there is another level. In fact, kind of the ultimate. You got a little peek of it there accidentally. The ultimate compounding is continuously. We're going to calculate this continuously. Now, how in the world would you do that? Well, now we're going to get almost to a calculus thing where you're dividing time up, a year up, into an infinite number of pieces, and you're going to calculate it an infinite number of times. Well, it turns out that if you're going to do this continuously, there is a calculation involving E. We can calculate the balance using the number E. So this is finally where you see the value of using E. If we take E to the 6% power, that's going to effectively give us the continuous amount. And it turns out, as you might expect, remember we didn't gain much going from daily to minutely, and we certainly are not going to gain anything noticeable, at least not to the penny. Now you'll notice there's a little bit of an increase if you go out a few more decimals, but to the penny we didn't really gain anything. But this is the key. This is how you do continuous compounding or any sort of continuous growth. You're going to find that this works with metabolism in your body. This works with any sort of organism or maybe bacteria that is growing essentially continuously. We can use this kind of a formula. So we're going to be wanting to watch for this word. Anytime we see growth that is continuous growth, or at least could be modeled with continuous growth, then we have a much simpler formula to use, and I think you would agree this formula is way simpler than the compound interest formula. And so we would use this sort of a formula in the future if we ever have continuous growth. So here's the continuous growth rate template. This would be a formula. You might recognize the formula looks a little bit like the just the A times B to the T. The only difference is instead of where B used to be sitting, we now have E to the K. And so this is the template for any sort of continuous growth problem that you might model with an equation. K is what we call the continuous growth rate. On the previous example, K was 0.06, which meant it was continuously growing at 6%. And it turns out then that when K is positive, that will be a increasing function, increasing exponential function. And when K is negative, then that will be a decreasing exponential function. And you just need to remember that when you go back to the other way that we sometimes write equations with growth rates, the other way to do this, if it's a per year or per day or any sort of a problem where you're growing at a particular unit of time, why then we would use this formula and we would use B for the growth factor. And remember, for this one, anytime B was between 0 and 1, it was decreasing. Anytime B was greater than 1, it was increasing. And now we've got a little different rule for K. When K is positive, it's increasing. When K is negative, it's decreasing. So it's going to be a little complicated to keep track of continuous growth rate, which is K, and then growth factors when you're doing like per year, per month type things with a growth factor of B. We're just going to have to be careful to know the difference between them. All right, so how about let's just start with some easier examples. If this was a problem given to you and your job was to find the continuous growth rate, I hope you would know to look no further than right here. The exponent of E is the continuous growth rate, and since that's a decimal point too, we would say this is a 20% increase. So whatever this thing is, it's growing at a continuous growth rate of 20%. This equation is starting with an initial amount of 5, just like the previous one, but this growth rate would be 30%. So this particular function has a 30% continuous growth rate that's increasing. And then the third one, This is an example where here we're starting at 5 again, but now here's an example where it's decreasing. Maybe this is a radioactive decay problem or some sort of a problem of metabolism. And so that negative 0.2 would be showing a 20% decrease. So it's exponentially decaying. Sometimes we use the words growth or decay. So these two are both growing, and then this one we might call a decay. It depends on the situation. If this is a science problem where you have radioactive decay, then this would be the type of number you would expect to see in a formula for continuous decay. What I would like you to do is to graph all three of these on your calculator using the same window, and there will be a question on the quiz regarding those later. Now let's talk about a population problem. If there's a population that increases from 7.3 million continuously at 2.2% per year, one thing we want to make sure we pull out of this, as soon as you see this word right here in a problem regarding exponential growth, we've got to be thinking of a formula with E in it. So as soon as you see that word continuous, we've got to be thinking of this sort of a formula. This is the formula that's going to be used anytime you see the word continuous. So just beware and be ready to watch for that. So first of all, the formula, if we use this template, would be that some quantity is going to equal the initial amount, which would be 7.3 in millions, times e to the, and since it's increasing, it's growing at 2.2%. Now we have to put that in a decimal, so we do want to write that as 0.022 to the t. There would be our formula. That would be the formula for the growth of this population according to the given information. And then estimating graphically when the population reaches 10 million. Graphically means we graph it on our calculators, and if you followed a previous lesson, you know that if it's starting at 7.3 million right there and it's growing exponentially, it's going to be doing something like this. And we can just graph y equals 10 here. And so this is just a general sketch of what your calculator is going to do. So you've got your exponential function and you've got your constant function, and your job is to find out when will the population reach 10 million. When would be this number right there. And that would be in years according to the problem here. So once again, I'd like you to do this on your calculator, and you can expect that to show up on a quiz in the near future. Here's a caffeine problem. Caffeine is something that once you drink it, it starts to decay. It starts to metabolize. And so once again, we see this word, it's a continuous rate problem. So clearly it's going to have the form of a quantity equals A times E to the KT. And it's leaving the body, so it's decaying or metabolizing at a rate of 17% per hour. And so the first part of this will be to write an equation. And so let me start with that. The quantity that's in your body at any particular time is going to be the amount that you started with, which I see is listed here as 100 milligrams, times E to the continuous growth rate. Well, this is actually a decay rate of 17%, so we want to write that as negative 0.17 t. So that would be the formula for this problem. We've got our initial amount 100 in the right spot. We know it's continuous. That's why we wrote it as an E problem. It's leaving the body. That's how I know it's a negative, and it's 17% per hour, so it's negative 0.17. And then the question is, how much caffeine is left in your body 8 hours after drinking a cup of coffee? So the last little piece here is to know what to do with the 8 to calculate how much caffeine is left or remaining in the body. Once again, I'll let you do that. You have enough tools at your disposal that you can solve that problem as well. And that will be on a quiz in the near future. Now let's go back and summarize. This was one of the calculations we did earlier. And you might remember where all these came from, hopefully, from the story. This would have a $sign on it. And I hope you remember where all these things came from, because there's a general formula that will work for any sort of compound interest problem. And it would be something like this. The balance that we calculate is always going to be the $1,500. $1,500 is sometimes called the principal. The principal is simply the initial amount that you start with. It could be an initial deposit. It could be an initial loan that you take out, depending on the problem. But it's the original amount of money, generally in any sort of a money calculation problem. So principal, and then you're always going to have one. One kind of stands for 100% because we always start with 1,500. So that's essentially saying, all right, we're going to start with 1,500, which is 100%. And then we're going to add a fraction of the interest rate. So that numerator, 0.06, you might remember, was the interest rate. R stands for the rate, or in money problems, many times it just goes by an acronym as annual percent rate. So that would be your interest rate. And then the denominator, that 525,600, that denominator was the number of times that we're going to compound it. So if we were going to compound it minutely, that's how many minutes were in a year. So that would be the number of times we're going to compound during the year. That's the number of compoundings, or number of calculations during the year. And then you might notice that the exponent was always the same as the number of compoundings. Now, there was another hidden variable that we didn't do. You might remember we started out by saying, oh, we're just going to do this for 1 year. Well, what if you do it for more than 1 year? Well, if you do it for more than 1 year, why then we would just multiply n times the number of years. So technically, all the problems we were doing earlier in the video, we're just taking that times 1 every time because we said at the beginning we would just do 1 year. So here you go. This is your compound interest formula for any sort of a problem that says your money is compounded daily or compounded hourly or compounded monthly, something like that. If the word compounded is in there and it's a unit of time, then we'd use this formula. However, there are a lot of accounts and interest rates and savings plans that are calculated continuously. So again, once you see this word, if it's a continuously compounded problem, why we're going to have E in it somehow. So we know this problem, because it's continuous, is going to have E in it. And we always start with the balance, or I'm sorry, you start with the principal. The balance is going to equal the principal that you start with. So this is the same. This is the same definition. So we have the principal, we're going to have the annual percent rate, and we're going to have the number of years. And so this formula will look very similar to the compound interest formula. However, we're replacing the innards of it with just e to a power in there. So sometimes I'll refer to this as the PERT formula because it kind of spells that word PERT. And this would be the formula. It's very simple compared to the other one for continuously compounded interest on a finance problem. Now earlier I mentioned that it may have been called a 6% interest rate back earlier, but a lot of those compoundings that we got, we ended up with more than 6%. And that's the difference between effective and nominal. The word nominal comes from the root word NOM in here, and it just means in name only. Nominal means in name only. So in other words, it's the percent rate that is given in the problem. So our particular nominal rate for this problem is 5%. It's called a 5% annual interest. It's called 5% annual interest, but we're going to find out that we actually get more than that. So since this is a continuous interest problem, we're going to use that PERT formula, principal times e to the RT. And we know that balance is always going to be, here's our principal, $1,000, times e to the 0.05t. And now we want to find the effective rate. The effective rate turns out to be what you really get when you do it continuously. It'll be a little bit more than 5% because of the continuous compounding. And so here's something we can think about. This is the formula that goes with that problem as stated. However, if we were doing this the other way, like if we're doing per year, per day, per minute, something like that, we would be doing the other formula. The other formula you might remember would have had b to the t in it. This would have been a times b to the t. So what I'd kind of like you to think about is what used to be in the position where b is in the other way that we calculate exponential functions. The growth factor has been replaced by e to the k power. And so it turns out that if you would calculate, and that t is extra there, if you would just calculate e to the 0.05 power, you would find out that the equivalent to that, e to the 0.05 power, would be a b value, or a growth factor of 1.05127. This is actually a pretty nice little way of calculating the effective rate. All you have to do really, I mean, it wouldn't matter whether it's $1,000, $2,000, $5,000. What's happening to that is right here. This is what is going to be done to that 1,000 or any other number that's there. So e to the 0.05 power turns out to be 1.05127. And notice it's a little bit bigger than the name. The name of this interest rate was 5%. But what you effectively get is 5.127%. That's a real nice quick way to find the effective interest rate. You just look at the inside of this formula and pick out the e to the power, whatever power it is. And that will produce a growth factor. And from that growth factor, you can clearly see that the effective rate, what you really get when you do this calculation, is you get a little bit more. You get 0.127% more than 5%. So this is what would be considered the effective rate. The nominal rate, of course, was just 5%. That was the name of it. Now there's one more example on your handout, example number 5. And by now you should have the tools and the examples to complete that on your own. And this will also see its way to a quiz in your near future. So that's it. There's a lot to handle there, and you may have to go back over a few things because I know there was a lot of things that were deep and went kind of fast. But once again, we'll be doing a lot of practice in class next time. And if you just go to Canvas, you should see the link to this video and then some other information about any quizzes or assignments that are due. Otherwise, I will see you in class.
In 525,600 minutes, how do you